Hi everyone. Welcome to my video. In this video, I will introduce Jimmer, a revolutionary ORM framework for Java and Kotlin. In nearly 20 years of practice, I have used too many ORM frameworks. This new ORM framework is the crystallization of my long-term thinking in this field. The framework supports two APIs, Java API and Kotlin API. Since the Kotlin API is shorter and more intuitive, this video uses Kotlin to explain. Don't worry, the functionalities of the framework's Java API and Kotlin API are same. Although this video is based on Kotlin, you can still develop projects in Java. In the documentation, all code snippets are shown in both Java and Kotlin code. The demo also supports two directories, Java examples and Kotlin examples. Jimmer can bring you two benefits. The first benefit is extreme performance. Jimmer does not use Java's reflection, so it can achieve high mapping efficiency. You can view the benchmark report through the documentation, which compares the efficiency difference between Jimmer and existing popular solutions. You can also view its source code in the benchmark directory of the project. This subproject uses an in-memory database, so it can be run directly without building an environment. This benefit can be well illustrated by a benchmark, so it is not the focus of this video. The second benefit is that the distinctive design brings powerful functionalities. Three aspects should be considered in ORM design. 1. Query. 2. Update. 3. Cache. Each aspect is aimed at object trees with arbitrary depth, rather than simple objects. This distinctive design brings convenience unmatched by other popular solutions. This is the topics of this video. 1. Object fetcher, query object trees with arbitrary depth. 2. Save command, save object trees with arbitrary depth. 3. External cache, cache object trees with arbitrary depth. 4. Dynamic table joins. 5. Paging query. 6. Quickly build Spring GraphQL applications. Note, this video only shows features that are unique to Jimmer, not features that all ORMs must implement. The first topic, Object Fetcher. Object Fetcher allows us to query object trees of arbitrary depth, and even recursive queries for self-associative properties. Before we discuss Object Fetcher, let's look at the simplest example without Object Fetcher. Let's switch to IntelliJ. This is the simplest example. Here, we create a query for books, execute it, and print the results. Inside the query, we first used a where clause to reduce the number of data returned. Finally, use the select clause to return the query results. A detail needs to be explained here. The select clause determines the return type of the query, so it must appear at the end. This style may sound unfamiliar to you, however, if you have ever used C#'s link, this style will be familiar. Our select clause is simple, with one simple parameter, table. This means that the query returns sum of simple book objects, without any associated objects that would require querying other tables. Now, execute the program. Later, it prints the result. We see that there are 3 book objects in the result. Another detail needs to be explained here. Each book contains its parent object reference store, but these parent objects only have an ID property. Why? The property store of book is a many-to-one association based on foreign key. In this case, the primary key of the parent table is actually the foreign key of the current table. We can get the ID of the parent object even if we only query the current table. Simple usage of Object Fetcher. Now, we want to specify the format of the returned objects, so we call the function fetchBy of the current object. First, we need all the scalar properties of the current book object. We can call the function allScalarFields. Book has a many-to-one association, the property store. We also want to query it. We can call the function store here. Inside it, we want to get all the scalar properties of the parent object. We can call the function allScalarFields. Book also has a many-to-many association, the property authors. We also want to query it. We can call the function authors here. Inside it, we want to get all the scalar properties of the author object. We can call the function allScalarFields. You can also specify filter for associated property. The property authors is a many-to-many property, that means it returns a list. Sorting a list is a meaningful operation. Execute the program. And later, it prints out the result. We see that the result is the same 3 books. But this time the results are more detailed. We see that for each book, the complete parent object can be found according to the many-to-one property store, and the complete set of associated objects author can be found according to the many-to-many property authors. Look for SQL in the logs. We found 3 SQL statements. The first SQL represents the main query. The second SQL means querying the parent objects through a many-to-one association. The third SQL means querying the lists of author objects through a many-to-many association. We can see that the third SQL uses the in clause, which means it's bulk operations, so there is no n+1 problem. Recursively query self-associated property. Now, let's query deeper object tree. This time we query the objects whose type are tree node. First, we use the where condition to query the node whose property parent is null. That is, query all root objects. Execute, wait a moment. There is only one root node, it is called home. We want to query the first level of child nodes, we can call the function child nodes. Execute, wait a moment. We can see that the first level of child nodes are queried, they are called food and clothing. We want to query the second level of child nodes, we can call child nodes inside the first level. Execute, wait a moment. We can see that more and deeper child nodes are queried. If we want to query the third level of child nodes, we can do so. If we want to query the fourth level child node, we can do so. Soon, we found that we were facing a problem. We could not assume the depth of the tree in the database. No matter how deeply nested your code is, it's useless. It's time to reveal our next weapon, recursively query. Keep only first layer and order it to query recursively. Execute, wait a moment. We see that the entire tree is queried. Recursion condition. The last question, we don't want to query the entire tree, but add recursion conditions to implement selective recursion instead of blind recursion. Taking the data we see here as an example, we only want to see the subtree of food, excluding the subtree of clothing. Okay, back to the code, add the recursive condition. Execute it again. This time, we still see the subtree of food, but not the subtree of clothing. The second topic, save command. Jimmer's data object is dynamic, it can to describe object tree with arbitrary complexity, such as partial object, complete object, shallower object tree, deeper object tree. Regardless of the data format, the user can save objects with a single function call. Jimmer uses the structure of the dynamic object itself to indicate the options of cascading saving, so there is no need to statically configure cascading saving options on the association mapping like other ORMs. Next, we will discuss the following 4 subtopics. 1. Save lonely objects. 2. Save the shallow object tree. 3. Save the deep object tree. 4. The save tree command of the Spring Shell project in the example. Save lonely object. Let me switch to IntelliJ. The function save here means to save an object, but it does not specify whether it is an insert or an update. You can specify whether the save mode is insert only or update only. However, in this demo, we don't specify and let the framework decide for itself. Please look at here, the object to be saved has no ID. Note that this does not mean null, in fact, ID cannot accept null value. It means the value of ID is unknown. Let's jump to the definition of book. We can see that 2 properties are decorated with the annotation key, name, and edition. This means that for the object whose ID is not specified, check whether the data already exists according to its name and addition, and decide whether it should be updated or inserted. If the framework decides to insert data, it must generate new ID value according to the annotation generated value. Execute, wait a moment. For the first run, the data is not exists, so insert operation is performed. Execute again, wait a moment. Now, the data already exists, so update operation is performed. Save shallow object tree. If the associated objects of the saved object only have ID, then only current object and its association with other objects can be saved, not the associated objects themselves. Okay, let's switch to IntelliJ. Now, set the associated properties for the object to be saved, but the associated object only has the ID. Execute, wait a moment. First, let's look at the update statement. We see that the foreign key is updated. Now, let's look at the last insert statement, and we see that some data is inserted into the table book author mapping, which is the middle table for the many-to-many association between books and authors. It inserts 3 pieces of data, because we specified 3 authors for the book. 1, 2, and 3. Now, modify the code. 3, 4, and 5. Obviously, if the program is executed again, 1 and 2 will be deleted, and 4 and 5 will be inserted. Execute again, wait a moment. First look at the delete statement. It deletes 2 pieces of data, representing 1 and 2. Then look at the insert statement. It inserts 2 pieces of data, representing 4 and 5. Save deep object tree. If the associated objects of the saved object contain non-ID properties, then 1. Not only the current object and its associations to other objects can be saved, but also the associated objects can be further saved. 2. The depth of the saved object tree can be unlimited. However, no matter how deep it is, the framework can handle all the details inside it. Alright, let's switch to IntelliJ. Here we want to save a book object. Its associated objects have non-ID properties. There is one detail that needs to be explained. By default, an exception is thrown if the associated object does not exist. The function setAutoAttaching all here indicates that all non-existing associated objects should be automatically inserted. Execute, wait a moment. Look at the SQL statement in the log. Update book. Insert associated Bookstore. Insert associated authors. Delete old associations from the middle table. Insert new associations into the middle table. In demo, there is an example called Jimmer SQL. Java project. Kotlin project. Alright, let's switch to the documentation. This example is a Spring Shell application. It supports a command save tree, which has 3 parameters. Root name, the name of the root node of the tree to save. Depth, the depth of the tree to save, excluding the root node itself. Breadth, the number of children of each node except leaf nodes. Here is an example where the node name is specified as my node, and the depth and breadth are both specified as 2. It means to save the following tree. The root node is level 0. These are level 1 child nodes. These are level 2 child nodes. Among them, in addition to leaf nodes, each node has 2 child nodes. Let's switch to the command line. Now we can create a tree whose root node is called my node, has a depth of 3 and a breadth of 3. We can see many insert statements. We can also use another command to query the tree. We see that this is the tree we just saved. Next, use the save tree command again to override it. This time, we specify 1 for both depth and breadth. Since the new tree is smaller, we see many delete statements. Finally, query the validated again. The result shows that the tree is replaced. The third topic is external cache. By default, the framework is just a very lightweight and powerful SQL generator without cache. However, users can attach any external cache. The framework only manages and coordinates the cache, and does not do cache implementation. So it does not affect the user's choice of caching technology. In the project example, all database-related examples have two operating modes. 1. No cache mode. 2. Cached mode. Please see documentation and examples to know more. Next, we will discuss these subtopics. 1. Multi-level cache. 2. Cache type. 3. Basic usage. 4. Data consistency. 5. Calculated property. 6. Calculated cache. 7. Data consistency of calculated cache. Multi-level cache. Multi-level cache is an important concept. When a certain level of cache cannot find some data, if there is a next level cache, the missing data will be loaded from the next level cache, otherwise, load from the database. Jimmer supports multi-level cache using Chain Cache Builder. Please see this example. In this example, 1. The first level is the cache inside the JVM, based on caffeine. 2. The second level is a distributed shared cache, based on Redis. Here, caffeine binder and Redis binder are user-implemented classes. Jimmer does not affect the user's choice of caching technology, so users need to implement these two binder classes. They act as adapters to specific caching technologies. There are a few jobs, but a one-time job, so they won't be discussed in this video. Please view the documentation and examples to know more. Cache type. Unlike other ORMs, Jimmer supports not only object cache, but also associative cache. The two are combined behind the scenes and can be used with object fetcher. So, the cache is designed for object trees with arbitrary depth, rather than simple objects. There are 4 kinds of cache. Alright, let's switch to documentation. 1. Object cache. This cache maps IDs to entity objects, which are simple objects without associations. Here are some examples. 2. Reference association cache. This cache is used for one-to-one and many-to-one associations, mapping the current object ID to the ID of the associated object. Here are some examples. 3. List association cache. This cache is used for one-to-many and many-to-many associations, mapping the current object ID to a list of associated object IDs. Here are some examples. 4. Calculated association cache. This cache is used for user-defined calculated properties. An example of this kind of caching is in another article. Let's jump to it. Here are some examples. Basic usage. By default, Jimmer does not use cache. So, developers need to configure cache for it. To save time, this video does not discuss how to configure cache, because it has already been discussed in the documentation and examples. Now, let's directly demonstrate the effect of cache. Switch to IntelliJ. This is a query for tree node object. The where condition requires parent to be null, which means the query root nodes. Use the fetch by function to specify the object format, fetch child nodes. Note, the function recursive is used here, which means querying the entire tree, no matter how deep. Execute, wait a moment. We saw many select statements, they query the whole tree layer by layer. Execute again, wait a moment. This time, we can see only one select statement. It's used to query root nodes. All the associated objects are already in the cache, so no SQL query is needed. Let's switch to the Redis UI. Refresh. We can see that there is some data in Redis. First, look at a data item object cache. Then, look at a data item of associative cache. Data consistency. Jimmer provides a solution to guarantee data consistency between database and cache. Developers need to 1. Use a database that supports binlog, and enable binlog. 2. Use a message queue, such as Kafka, and create a topic. 3. Use some tools such as Maxwell, Canal, Databooz to push the binlog changes to the message queue. 4. Listen to the message queue in the application, call Jimmer's API to clear the affected caches. Core value provided by Jimmer: not only the affected object cache can be deleted, but also the affected associative cache can be deleted. Okay, let's switch to IntelliJ. There is a class called Maxwell Listener. It has a function, which is decorated by the annotation Kafka Listener. It is listening on Kafka. Every time a message arrives, the table name is first parsed. Check whether changes of this table should affect some caches. If so, call Jimmer's API, and validate by binlog. For the 3 cases of insert, update and delete, the parameter passing is slightly different. Finally, commit the Kafka consumer offset. Execute, wait a moment. Clear the log. This is SQL tool on the right side. Modify book whose ID is 12. Its foreign key stored is 2. Change it to 1. Execute SQL. Look at the output of IntelliJ. The object cache for the current book is deleted. For the old parent object whose ID is 2, its one-to-many association cache is deleted. For the new parent object whose ID is 1, its one-to-many association cache is deleted. The many-to-one association cache for the current book is deleted. Calculated property. Calculated property is not part of the cache. However, in order to explain the calculated cache, the calculated property must be explained first. For complex business calculation, you may need to develop specialized business components, and may even use OLAP-related technologies. However, for simple business calculation, you can directly make entity type support calculated properties. That's what's being discussed here. In our case, 1. The Bookstore has a one-to-many association, bookstore.books. 2. Book has numeric property, price. So, we let the Bookstore support a calculated property, average price, which represents the average price of all its books. Let's switch to IntelliJ. Here we see a class called Bookstore Average Price Resolver. It implements the interface kTransient Resolver, accepts SQL client through the constructor. Look at this function, resolve. It has 2 parameters. IDs, a collection of IDs for a batch of bookstores. Current database connection. The function returns a map. Its key is the ID of the bookstore, its value is the average price of all books in the bookstore. The logic is a group query. Using the where clause, filter the ID of the bookstore. Use the group by clause to group by bookstore ID. Use the select clause to return 2 columns. The bookstore ID and the average price of the book. Then, execute the query on the current database connection. Finally, convert the returned list to map, and return it. Well, let's jump to the definition of the book, which has an property named average price. This property is decorated with the annotation transient. You can specify argument for this annotation. Once the argument is specified, the property becomes a calculated property. Here, the argument is the class we just made. Switch to the main function. Here, we query the bookstore and explicitly require the calculated property average price. Execute, wait a moment. In the result, we can see the values of the calculated field. Calculated cache. Now that we've introduced calculated properties, it's time to talk about calculated cache. Like other caches, calculated caches require configuration to be enabled. To save time, this video does not discuss how to configure cache, because it has already been discussed in the documentation and examples. Let's switch to IntelliJ. Unlike the last time, this time we have enabled calculated cache. Execute, wait a moment. We can see 2 SQL statements. 1. Query bookstores. 2. Calculate the average price for each bookstore. Execute again, wait a moment. This time, we can only see the first SQL statement, because the average price of the bookstore has already been cached. Let's switch to the Redis UI. Refresh. What we're seeing now is the calculated cache. Data consistency of calculated cache. Unlike associated properties, since calculated properties use developer-defined rules, their consistency cannot be guaranteed in a fully automatic manner. It requires the help of developers. Take the bookstore.average price here as an example. 1. If the foreign key of a book is modified, the average price caches of the two parent objects before and after the modification need to be invalidated. 2. If the price of a book is modified, the average price cache of its parent object needs to be invalidated. Let's switch to IntelliJ. See the class Bookstore average price resolver again. This time, we added constructor logic to it. First, monitor the one-to-many association, bookstore.books. If the bookstore's book list changes, the bookstore's average price cache needs to be invalidated. Then, monitor the book object. On the premise that the foreign key has not changed, check whether the price has changed. If changed, the average price cache of the parent object needs to be invalidated. Execute, wait a moment. (1) Modify the price of the book. Clear log. In the SQL tool on the right, modify the price of the book. We see that the calculation cache of the parent object is deleted. 2. Modify the foreign key of the book. Clean up logs. In the SQL tool on the right, modify the book's foreign key. We can see that there are 6 cache delete operations performed automatically here. The first 4 we have discussed, ignore them. The last 2 are the behavior we now expect. The average price caches for both parent objects before and after the modification are deleted. The fourth topic, dynamic table joins. Table joins in Jimmer are implicit and dynamic. This is designed for dynamic queries. Even if there are some conflicting table joins in different code branches, in the final generated SQL, they will be merged into one. Alright, switch to IntelliJ. Here is a function find books, all of its parameters is nullable. These two where clauses are inside the conditional judgment, so this is a dynamic query. When store name is non-null, add the first where condition. The store here means inner join, then filter the name of parent object. For demonstration purposes, we print the log. When store website is not null, add a second where condition. The store here means inner join, then filter the website of parent object. For demonstration purposes, we print the log. Next, we used order by and select, but that's not our focus right now. Call it in the main function. All the parameters are specified as non-null values. Execute, wait a moment. We see those 2 log messages about joins are printed. However, let's look at the SQL statement. We can only find one join clause. The fifth topic, paging query. In the paging scenario, developers only need to focus on querying the actual data, and the query on the number of rows is automatically generated and optimized by the framework. To save time, this video only show how the count query is automatically generated. We do not explain how it is optimized. Please view the documentation to know more. Let's switch to IntelliJ. Here we create a query with dynamic conditions. It returns entity objects. However, instead of executing the query immediately, we assign it to the local variable, query. Next, we use the function, reselect, to adjust. This function will not affect the old query object, but create a new query object. The new query can return the total row count. We assign it to the local variable, count query. Next, we execute the count query to get the total row count. Let each page contains 5 rows, get the total page count. Loop for each page, query data for each page. Look at the function limit. It does not affect the original query object, but creates a new query object. Execute the new query object, You can get data of current page, not all. Execute, wait a moment. We see that total row count is 9, and total page count is 2. This is data of first page. This is data of second page. Then look at the log, we can find 3 select statements. 1. Query the total number of records. 2. Query the data on the first page. 3. Query the data on the second page. Among them, the first query is the count query automatically generated by the framework. The sixth topic, quickly build Spring GraphQL applications. Spring Boot has introduced Spring GraphQL since 2.7. Jimmer provides specialized API for rapid development of Spring GraphQL-based applications. Next, we will discuss 2 subtopics. 1. Query. 2. Mutation. Query. As you may have noticed, Object Fetcher and GraphQL queries are highly similar. Their similarities, they both focus on how to query object trees of arbitrary depth. Their differences, Object Fetcher extends SQL, let SQL also have this ability, GraphQL exposes this capability through HTTP API. They are so similar, in fact, that they share the same underlying code. Therefore, they have some of the same important capabilities, for example, using the powerful external cache. The only caveat is that Object Fetcher supports recursive queries based on self-associative properties, which the GraphQL protocol has not supported so far. The topic discussed here is not how to query aggregate root objects. Whether or not GraphQL technology is used does not affect how these queries should be implemented. This video will not discuss them. The focus here is how to query the associated properties of an object. For Spring GraphQL, it is how to quickly implement methods decorated by batch mapping. In order to quickly implement these methods decorated by batch mapping, Jimmer provides 3 loader objects. 1. Reference loader, quickly implement one-to-one or many-to-one association properties. 2. List loader, quickly implement one-to-many or many-to-many association properties. 3. Value loader, quickly implement calculated properties. With the help of these objects, quickly supporting GraphQL queries is a simple task. Alright, let's switch to IntelliJ. First, let's look at an example of reference loader. Here is a class named bookController. Here is a function, store. Its name, parameters, and return type follow Spring GraphQL conventions. A detail needs to be explained here. The parameter type is forced to be defined as java.util.list, not the Kotlin list. This is caused by a bug of Spring GraphQL. I have submitted this bug to Spring GraphQL. The issue number is 454. Inside the function, use the reference loader. Use the list loader to expose a many-to-one properties through the GraphQL protocol, book.store. Then, let's look at an example of list loader. Here's a function, authors. Its name, parameters, and return type follow Spring GraphQL conventions. Inside the function, use the list loader to expose many-to-many properties through the GraphQL protocol, book.authors. Finally, let's look at another example of a calculated property. Switch to Bookstore controller. Here's a function, average price. Its name, parameters, and return type follow Spring GraphQL conventions. Inside the function, use the value loader to expose calculated property through the GraphQL protocol, bookstore.averagePrice. The implementation of other properties is exactly the same. We don't need to browse all the code. Okay, start the server. Open a browser and visit http localhost 8080 GraphQL. Enter the query request. Execute. Look, we got the desired result. Mutation. From the previous introduction, we know that the save command can save object through one API call, no matter how complex it is. In GraphQL, if an argument needs to accept complex type, input type must be used. You can consider input type as a DTO mandated by the GraphQL protocol. Therefore, you only need to convert the static input DTO into the dynamic object tree required by the save command, and all the problems can be solved. Note, while the save command is a powerful enough solution, sometimes your modification behavior may be so simple that a more lightweight approach is desired. In this case, You can modify the database using other simple ways not discussed in the video. Okay, let's switch to IntelliJ. First, take a look at this class called bookInput, which is required by the Graphql protocol. This class contains one function, toBook. This function is responsible for converting the current input object into entity object tree. It is the only value of this class. Now let's switch to the class bookController. Scroll down. Now, we can see a function, saveBook. Its parameter type is the book input we discussed. Inside it, we call the input object's function, toBook. Convert the input to entity object tree. No matter how complex the transformed entity object tree is, we can save it in one sentence. Okay, start the server. Open a browser and visit http localhost 8080 Graphql. Enter the mutation request. Execute. Okay, this mutation is done. Thanks for watching. If you like this project, please give it stars and use it in practice.